Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the last lecture of module 5 in which we were discussing about refraction and reflection seismology. Let's move further and talk about multiple channel data geometry, and also we will be talking about common midpoint stacking and normal move out correction. Then we will discuss about deconvolution. Finally, we will summarize today's lecture. As far as the recap of previous lecture is concerned, we learnt that for a continuous increasing velocity model, at the deepest point, the turning or the bottoming depth Zp, the velocity is reciprocal of the ray parameter. That means ray parameter will be equal to 1 by velocity. The distance travelled by the ray as a function of ray parameter can be written as twice integral from 0 to bottoming depth, that is Zp, tan of incident angle dz, that will be equal to, in terms of ray parameter and the velocity, integral over 0 to Zp in bracket 1 by v square minus p square dz. Time taken to cover distance xp by the ray can be written in the form of vertical and the horizontal ray parameters. So the total travel time will be equal to the product of horizontal ray parameter multiplied to the horizontal distance covered by the ray plus the vertical ray parameter multiplied the vertical distance covered by the ray in each of the layers. The function tau p, that is the intercept time, is called the intercept slowness representation of the travel time curve because we are representing the intercept time as a function of ray parameter. P is the ray parameter which can be found from the slope of the travel time curve, that is t, as a function of offset distance. And if you take the derivative of intercept time, that is a function of ray parameter, if we take the derivative of the intercept time with respect to the ray parameter, then it will be equal to the minus of the offset distance. The head wave maps into a point and hyperbola maps as ellipse on tau p plane. That is what we learnt in the previous lecture. Now let's start with the lecture today. We are going to talk about multiple channel data geometry or multi-channel data geometry, in which different kind of receivers, or you can say multiple sources and the multiple receiver positions, are used to increase the signal to noise ratio. And while using the multiple source and the receiver, so that we can sample the same point on the reflector multiple times in order to get high amount of signal to noise ratio. If you look at this particular example that is depicted in this diagram over here, here you can see there are 8 receivers and a single source. So source is over here, these are the receivers at different positions, and each time the source is moving rightward, one receiver is spacing at a time, and we are getting 8 traces while we are exciting the source. So each time when you are exciting the source, you are getting 8 traces from each of the receivers. That means one receiver is recording 1 trace at a time. So total number of receivers are 8. So 8 traces are being recorded by a excitation of the source. So eventually what is happening, at each time you are sampling a point on the reflector such as this one, and then each time you are basically sampling each point 4 times. That means the total fold is 4. That you can say we are producing 4-fold coverage using this data geometry, which means that each point is being sampled 4 times. That means when you will stack or take a average of the traces that are recorded 4 times from a single point, then you will get the average trace, which will be having a good amount of signal to noise ratio. The assumption that we are considering, the earth has layered depth variations in seismic velocities, which means earth is layered and it has the continuous variations in seismic velocities. And if you look at this diagram, here there is the receiver position, this is the source position, and if we consider this as an origin where x is equal to 0 and the depth is increasing downward, and here you have the x, and the receiver is r distance away and the source is f plus r distance away from the origin, and this is your horizontal interface. So when the source is activated, then the ray is traveling down and being reflected from the horizontal interface, and after the reflection it is recorded at the receiver. Now in order to get the value, or you can say the reflection from this particular point, this point is lying in the midway between the source and the receiver. So for a flat layered model, these seismograms have same point known as midpoint halfway between the source and the receiver. And this same point is being sampled multiple times by different data geometry or the different kind of gathers, and we are having this midpoint. If you want to calculate the position of the midpoint, that can be represented by m, and that will be equal to s plus r by 2, and that then also you can calculate offset, that is equal to s plus r is represented by f. The seismogram that we are recording can be represented or can be identified by source and the receiver position, that is the one way, and another way is you can identify it by the position of the midpoint and the offset. So you can see the source direction over here, source axis is over here and the receiver axis is perpendicular to it. Likewise, the midpoint axis is 45 degree from the receiver axis, or you can say in the midway between the source and the receiver, and the offset is also the 45 degree away from the source axis. So if you want to identify a particular point, these are all the midpoints, or you can say these are the common midpoint gather, because common midpoint gather scheme is very important in the case of oil and gas industry, and the application of this kind of gather is vast in the field of oil and gas exploration. So we are going to gather all these points. These are the midpoint gathers, and these midpoint gathers are representing a particular seismogram, or you can say these midpoint gathers or these individual midpoints are being sampled by an individual seismogram, and that seismogram, if you want to identify from a CMP gather, then it can be identified by either the source and receiver position or the midpoint and the offset position. So that will be either this value over here, this is the this is the source over here, and for this particular position this is the receiver. Likewise for the offset and the midpoint you can do the same. These are some of the gathers that can be used to sample the interface, or you can say the reflector. One is the common receiver gather, another is the common source gather, third one is the common offset gather, fourth one is the common midpoint gather. So in the common receiver gather, there is one receiver and there are the multiple sources. In common source gather, the source is one, the receivers are multiple. In common offset gather, the source and the receiver offset is same each time, and in common midpoint gather, the sampling point or the midpoint is the same. The common offset gathers are handy for small scale projects, since in the travel time equation, that is the travel time equation, Tx square is equal to x square by v naught square plus t naught square. This t naught is the two-way travel time for zero offset distance, and v naught is the top layer velocity, x is the offset. So this is very handy for a small scale project, because in common offset gathers the x naught is known, or you can say the offset is known because it is same each time, and v naught is constant. So you can say the x and v naught are constant, and this is a good approach for finding the top of a near surface layer, that means the bedrock. Now let's understand about common midpoint stacking and the normal move out correction. We are going to focus on common midpoint. In short, it is known as CMP gathers, since its application is quite common in oil and gas industry. Our goal is to find a way to suppress head waves, direct waves, surface waves, air waves, and multiple reflection. So the multiple reflection are shown over here. This is the peg-leg multiple, this is near surface multiple, here you have double path multiple, and here do you have the primary reflections. This is not the multiple. So what we want to do in order to get common midpoint gather, the aim of common midpoint gather is to suppress the direct waves, surface waves, air waves, head waves, and also all the multiples that might be arising during the data collection. And we want to emphasize on the primary reflections. So the multiples, if you want to understand, these are also the reflected waves, but they have reflection like more than one time from the reflectors before recording in the geophone. Our primary aim is to enhance the primary reflections and suppress everything else. Reflections have hyperbolic travel time curves, so these are different from the head waves, surface waves, and the air waves, because these waves have linear travel time curves. Consider a reflection whose variation in travel time with offset is the normal move out, where T naught, and this should be V bar, that is you can say the average velocity or the root mean square velocity, are the vertical two-way travel time and the RMS velocity. So if you look at this equation, the Tx is being subtracted by T naught on the both sides. So you can see this particular time is zero offset two-way travel time, and that will basically give you the how much is the time that need to be moved out from the travel time, so that we can have a proper stacking of your data, that we are going to see in the normal move out correction. So if each trace is shifted forward in time by the appropriate normal move out, so if you look at this diagram here you have this direct wave, you have head wave, and you have reflected wave. Direct wave and the head waves are having the linear variations with respect to time and the offset, and the reflected wave is hyperbolic in nature. So what we are going to do, we are going to shift each trace by their normal move out, that means by the value of zero offset two-way travel time, and then when you will stack them together, what will happen, the head waves, direct waves, and maybe the ground rolls will be having the destructive interference, and they will basically average out destructively and will give weaker signals onto your data section. But the reflected wave, that is having the constructive summation, so it will be having the enhanced signal onto your record section. So by contrast, arrivals with different move outs such as the direct wave do not align. Multiple reflections do not align because they reflected off shallower interfaces than primary reflections with a similar arrival time and thus have a lower RMS velocity. If the traces are added after this time shift, the resulting sum in theory is the single trace that would have been recorded at zero offset with coincident source and receiver. Reflection that was aligned is in phase on all traces and thus sums constructively and give a strong arrival. By contrast, other arrivals are out of phase and thus sum destructively, yielding weaker arrivals. The process of time shifting and then summing the traces with different offset for a given midpoint is called common midpoint stacking. So this is a typical diagram to understand the normal move out correction and hence the velocity analysis in CMP stacking. So this is the expression that we are using where you can see there is the velocity term here and we use different velocities to align our hyperbolic traces and we can use v1 velocity, we can use v2 velocity, we can use v3 velocities. Likewise, we can use many values of velocities to basically do normal move out corrections. So at v1 velocity, the hyperbolic reflection hyperbola may be something like this. At v2 it will be like this and v3 it may be like this. So we need to choose a correct velocity in order to do our velocity analysis. So what we do at each velocity, we basically compute a cross power values and then plot it with respect to their velocities. So at V1, V2 and V3 we can see at V1 this is the value of the cross power, at V2 this is the value of the cross power, at V3 this is the value of the cross power. Wherever at whatever velocity the cross power spectrum becomes maximum, or you can say wherever we can get the peak power at whatever velocity, that particular velocity is estimated to be the correct stacking velocity. So, to amplify the reflection, we sum or stack the traces with a common midpoint along a hyperbolic trajectory. We can try values for V bar until the maximum cross power is obtained. So, this particular velocity is known as the stacking velocity. In this case, V2 is corresponding to the maximum cross power. So, that will basically be used to align our traces and then for the stacking purposes. So this is the illustration of forming a zero offset section by common midpoint stacking, and this particular diagram is representing the stacking for different midpoints. So you can see this is the midpoint 1, this is the midpoint 2, this is the midpoint 3, this is the midpoint 4, likewise. And for each of the midpoint, we have these traces like trace 1, trace 2, trace 3, trace 4, trace 5, trace 6. And this is the reflection hyperbola that is going from each of these traces for midpoint M1. Likewise, for M2, we have this hyperbola. For M3, this is the hyperbola. For M4, this is the hyperbola. So when we are applying the velocity analysis after the normal move out correction, then you can see these traces are basically coming at the position B, that is the zero offset for the midpoint M1, and then likewise this is the zero offset time for the midpoint M2, and this is M3, this is for M4, and then we can join them together to see the location of the reflection. So this technique, common midpoint technique, we have learned for the flat layer case, and you can understand that in case of the dipping interface like this one, there will be no common midpoint. But still, this techniques works quite well in case of dipping interfaces as well. Now let's understand the process of deconvolution. If you will see, there is a source, and that when it is excited, it releases a source pulse. And that source pulse basically travels through the different layers of the earth and then comes back onto the receiver. So what is basically happening? These are the different layers of the earth. This is can be represented by this geological section. And this geological section is basically represented by the reflector series, that is the reflector series, and each of the interface is having certain spike, or you can say certain impulses at times corresponding to the arrival times of the reflections with amplitudes given by the reflection coefficients. So these are given by the reflection coefficient. So when source pulse, or you can say the input pulse, comes to the reflecting series of the earth, then it gets convolved with this reflectivity series, and finally what you will get a seismic trace. This wiggly lines, collection of the wiggly lines, or you can say the collection of the wiggles in the seismic traces. So what we do, we attempt to perform deconvolution because input pulse has been convolved with the reflector series and then it has given the seismic trace. Our aim is to find this reflector series. So in order to find so, we need to perform a reverse operation that is known as deconvolution. So deconvolution attempts to spike the wavelet in the data, revealing the reflector series. So the resulting seismogram, that seismogram or the seismic trace, is being represented by ST, and the wavelet is represented by WT in time domain, and the reflecting series is represented by RT in time domain. So the ST, the seismogram, is equal to the convolution of the wavelet and the reflective series of the earth. So when we do the Fourier transform, that can be converted into the frequency domain, and in frequency domain the convolution equals the product of the Fourier transform. So when we perform the Fourier transform of ST and WT and RT, then we can write ST is the product of the wavelet and the reflectivity series in the Fourier transform or in the frequency domain. If suppose this W omega, which is the wavelet, becomes the delta t, that is the direct delta function, then what will happen? You can say your seismogram will become equal to the reflectivity series of the earth. So that is what we want. We want our seismogram to show the reflectivity series of the earth. So, but what actually happens in the case of real earth situation, the physical source is not a delta function. The seismogram can be manipulated mathematically to simulate such a wavelet. So this particular value will not be a direct delta function, but we want to make it a direct delta function. So in real earth situation or when we have a seismic source, then it doesn't show the delta function. We want to basically perform some mathematical operation so that we can eliminate this source wavelet from here or the input signal from there. For this purpose, we do inverse filtering and we want to calculate inverse of the input pulse W inverse T, and when it will be convolved with the wavelet, then it will yield the delta function. So basically W inverse T will be convolved with WT, then it will give the delta function. So applying this filter, which spikes the wavelet, leaves only the reflector series. So what we do, we multiply with W inverse T with on the both of the sides. Then what you will get, this W inverse T, when it will convolve with WT, then it will remain with RT, that is the reflecting series of the earth, and it will be equal to this thing. So we will have to design the inverse filter W inverse T. Because this operation is the inverse of the convolution, it is called deconvolution. To create the inverse function or the inverse filter, we know that W inverse omega, W in omega is equal to 1. So the transform of the inverse filter is just 1 by W omega. Hence deconvolution can be done by dividing the Fourier transform. So just you will have to divide by the W omega on the both sides in the Fourier transform. So this is the summary of today's lecture. It is an use of the multiple source and receiver location so that points on the reflecting interfaces are sampled repeatedly. That is done for multi-channel data collection. Each trace we get is a record of the displacement or pressure as a function of time. So whatever trace that we record on the receiver, it can be a function of displacement, pressure, or as a function of time. Individual seismogram is specified by source and receiver position or midpoint and offset. Sorting and combining of data can be done using common midpoint gathers, common offset gather, common receiver gathers, and common source gathers. NMO correction for CMP stacking can be done using this particular expression where we try to find this V bar or the RMS velocity using the velocity analysis where we see the cross power spectrum at different velocities. Wherever the cross power spectrum reaches its peak, corresponding velocity is the final stacking velocity. The convolution to get reflectivity series in time and frequency domain are this we have just learned in the previous slide. These are the references, and in the next module we are going to start with the rays traveling in the spherical earth. So thank you so much. Bye bye.